So as you know, semiconductors are a special class of material. If you see most of the electronic devices, okay, they use semiconductor. Okay, so why semiconductors are so important? Okay, what makes them different, these material, from metals and insulators? Okay, so let us discuss. Okay, so first thing is electrical conductivity. So what is electrical conductivity? Okay, so electrical conductivity shows ability to flow current. Okay, ability to flow of current. Okay. So we know conductivity, okay, is reciprocal of resistivity. So if we see the resistivity values, okay, for metals, okay, they are less than 10 raised to power minus 3 ohm per centimeter. Okay, for example, silver and gold are in order of 10 raised to power minus 8. Okay, the resistivities are very low for conductors. Okay, and if you see resistivity of insulators, okay, they are greater than 10 raised to power 8 ohm per centimeters. Okay, while your semiconductors, they have intermediate electrical conductivity between conductors and insulator. Okay, so they have a less conductivity compared to metals. Still they are so useful. Okay, why they are so useful? So the one thing is there, that for example, if you say silicon, okay, so the electrical conductivity of silicon is pure silicon, 10 raised to power 10 raised to power 5 ohm centimeter. Okay, in pure form, at room temperature. Okay, so T is equal to 300 Kelvin. Okay, the resistivity of silicon is 10 raised to power 5. Okay, but the advantage we have with semiconductors is that we can modulate their conductivity for wide ranges. Okay, so suppose if I dope this semiconductor with some impurity atom, okay, I can modify this electrical conductivity. Okay, I can get a wide range of resistivity values by just doping or just by shining light on these materials. Okay, for example, this is not possible with metals. Okay, with metals we cannot play much, okay, with the electrical conductivities. Of course we can make alloys, okay, but then the order of magnitude, okay, the change in resistivity, the order of magnitude what we get in the case of semiconductor, okay, is not possible with metals. Okay, and the second thing is that this is the first thing. Okay, so we get a wide range of conductivity values, okay, with doping. Okay, or we can say modulated, okay, modulated conductivity ranges. We can modify conductivity ranges. This is the one thing which is make them different than metals. Okay, second we see that they semiconductor provide control flow of current. Okay, that's why they are used in electronic devices. For example, you say diode. Okay, if you join the two semiconductor, okay, P and N, okay, we make diode, and diode only allow current in the one direction. Okay, that means we can control the flow of current. Okay, such thing is not possible with metal. If you join two metal, nothing will happen. Okay, so joint of metal is a very limited applications. Okay, while if you have a semiconductor, okay, this diode, okay, that is a variety of applications. Okay, many type of diodes are formed. Okay, LED, solar cell, they have many application, circuit applications also. So so that is why, because we can control the flow of electron, okay, in electronic devices. So the second important point is with semiconductor is control flow of current, okay, in electron devices. Okay, we can achieve, okay, can be achieved. Control flow of electron current can be achieved in electronic devices. Okay. For example, if you make say tiny transistor, okay, so we apply a simple biasing, we can make input resistance very low, output resistance very high. These type of capabilities, okay, is not available with metals. Okay, metal contacts are very limited use, like you know Seebeck effects. Okay, so this is one thing. Now I want to discuss how resistivity and conductivity of semiconductor is different than metals. Okay, so for example, I say metal. Okay, so if I take metal, okay, the resistivity of metal, okay, increases with temperature. So if I say, if you just check the graph, you may have studied this graph. Okay, so resistivity of metal is the metal. Okay, varies as a increases as a proportional to T at certain range. Okay, at low temperature, it may be proportional to T cube or proportional to T5 also. We will discuss, then we will discuss this band theory of solids. Okay, so this is the graph of metal. Okay, resistivity with temperature. Resistivity of metal increases with temperature. While if you see semiconductor, okay, so semiconductor, if I take resistivity graph with temperature, okay, so the resistivity of temperature, the resistivity of semiconductor decreases with temperature. Okay, that means this for semiconductor. Okay, that means they show negative temperature coefficient of resistance. Okay, so the resistance decreases or resistivity decreases with temperature, where they show positive temperature coefficient of resistance. Okay, so this is the some differences. Okay, now question is, why some material have a high conductivity? Okay, why some material have a low conductivity? So for that, let me discuss conductivity, expression for conductivity. Okay, so conductivity of solids. Okay, why some material has low conductivity? So conductivity of solids, ये मिटा दूं सब?
Yes, sir.
Okay. Now if I say a solid cylinder, okay, solid block, okay, say its length is L. I want to know how conductivity is defined. Okay, what is the definition of conductivity, or what are the factors which define conductivity? Okay, say this is a L. Okay, and I'm applying now a potential, a voltage across this conductor. Okay, conductor or solid block. Okay, say its cross sectional area is A. Okay, so when I apply this voltage, okay, this voltage will create a electric field inside this material V by L. Okay, and because of this electric field, okay, this electric field will apply force. Suppose I'm considering in this block we have only electron and charge carriers. Okay, we have electrons. For the moment, I'm only discussing these are only electrons. Okay, so as we apply voltage, okay, it's the direction of current, and electron will flow opposite to the direction of current. So because of this electric field, the electron will start following. Okay, and if I say current I, so if I want to calculate the current density, so I can say current density J is I by A. Okay, and also we know the resistance of the material is rho L by A. Okay, so if I want to calculate electric field,
Sir, sir, ये जो voltage, you have applied voltage, and due to
एक
this
मिनट
the
तुम्हारी आवाज स्लो आ रही है.
electrons are flowing. Hello,
हाँ बोलो.
sir. I am saying that due to application of voltage, the
Your voice is
electrons
very
are.
less. I don't know why. Just अब बोलो.
Hello,
हाँ
hello. अब clear है, sir?
हाँ अब क्लियर है.
Okay. Sir, I am saying that due to application of voltage, the electrons are moving from right to left.
हाँ,
यही रीजन है सर, मतलब इलेक्ट्रॉन्स के मूव करने का।
फोर्स लग रहा है ना, चार्ज इलेक्ट्रिक फील्ड है,
यस
ये
सर।
वोल्टेज इलेक्ट्रिक फील्ड क्रिएट कर रहा है, और इलेक्ट्रिक फील्ड के कारण फोर्स लगेगा चार्ज पार्टिकल पे। फोर्स इज गिवन बाय क्यू ई।
क्यूई। यस सर।
ओके,
ओके सर।
so so our extra electric field is the direction. Okay, so force will be opposite direction, so they will opposite direction, electron will move.
ओके। ओके सर।
Okay, so now I can write expression for V. Okay, so I know I is equal to VR. Okay, so so V by L. Okay, so if I calculate uh, V is equal to IR. Okay, IR upon L. So I we know I can write J A R upon L, and if I put the value of R here, so J A R is rho. Okay, L by A. Okay, so A cancel, L cancel, so I got J equal to E by rho. Okay, which can be written as 1 by rho is sigma, so sigma E. Okay, so the relation between current density and conductivity is given by this. This is also another form of Ohm's law. Okay, so if you so this is the J value. Okay, so say this is the equation number 1. Okay,
Sir, how I equals to V into R you have written, sir?
V equal to IR. Sorry, V equal to IR. V equal to okay. आगे चले, यहाँ तक क्लियर है? ये एक्सप्रेशन तो पता ही है सबको, you तो many time you use J equal to sigma E. Okay, now suppose this block has a n free charge carriers. Okay, capital N free charge carriers. Okay, so with application these charge carriers are moving, so I know my current is I is equal to dq by dt or q by t. Okay, q by t. So there are n free charge carriers. Okay, and electrons, so their total charge will be q. This charge q is electron charge, and the number is n. So these charges are moving with time t. Okay, and suppose they are moving with the velocity v. Okay, so velocity v means I can write velocity is the L by t. Okay, so I want to write this in an expression of current in terms of velocity. So I can write now I is equal to qn, and I'm replacing time with velocity. So I can write t equal to L by v. Okay, L by v, and if I want the current density J, that is I by A, that will give me qn v L A. Okay, so L is the length of the this specimen. Okay, and A is the cross section area, that total become volume. Okay, so I say free charge carrier density, so N upon LA, okay, is N upon volume. Say this is volume. Okay, and this is equal to charge carrier concentration or charge carrier density. Okay, so I can write instead of this one J equal to q small n, okay, into velocity. So this is my second expression for current density. Okay, say this is my equation 2. Now equate both these equation. Okay, will give you the expression for conductivity. So now if I equate both these equation, sigma E is equal to q and concentration, velocity, and sigma E will be q and v by E. Okay, so velocity upon electric field क्या होता है? Velocity by electric field, mobility. Okay, this will give you the mobility. So q and mu, So this is the expression for conductivity. You can write Q instead of Q, you can write electron charge also. You can also write sigma is equal to, because here charge carriers are electron. So Ne mu or En mu, Ne mu. Okay. So this is the well-known expression for conductivity. Okay. So why I'm deriving this expression? Okay. Because we are differentiating based on the conductivity. Okay. We are comparing the semiconductor on base of conductivity. So I want to discuss here why some material have a high conductivity, some material have a low conductivity. So you can see the conductivity is governed by two factors. Okay. So number one factor is free charge carriers, concentration of free charge carriers. Concentration of free charge carriers. Okay. And second thing is mobility, electron or charge carriers mobility. Charge carrier mobility. Okay, these are the two primarily factors. Okay, primarily factors. Okay, which govern our conductivity. Okay, now in the case of metal, okay, the concentration N is very high. Okay, if I want to compare two materials, okay, so mobility, there will be, of course, there will be difference in mobilities. Okay, but difference in the mobility will be not many orders. Okay, there will be one order, two order difference in mobility, but because there is a variation in concentration of charge carriers. Okay, very high variation is there in the case of charge carrier. Okay, so metal may be 10⁵ or 6 order more than semiconductors. Okay, they have more charge carriers in metals. That's why they have very high conductivity compared to your semiconductors. Okay, now question is why why they have more charge carriers. Okay, charge carriers कहाँ से आते हैं? You have valence band or valence electron. When you need to supply energy, they become conduction electron. So why metals have a very high free charge carrier density, while your semiconductor insulators do not have a very high values of charge density? That depends on the bonding. Okay, so there are primarily, so which determines the concentration. Okay, this is bonding. Okay, so if you have ionic bonding, okay, ionic bonding such as NaCl. Okay, so this is a very strong force. In ionic bonding, you have a very strong coercive forces. Okay, so you need more energy to make electron free because these are strong bonds. If while in the second case, if you say metallic bonding, okay, metallic bonding, which we see in the case of our metals. Okay, these are weak bondings. Okay, so you can easily you can get free electrons in the case of metals. Okay, but this is the ionic bonding. While you see semiconductors, okay, in semiconductor we generally discuss covalent bonding. Okay, covalent bonding. If we take our silicon, germanium, okay, these all have a covalent bonding. Okay, so this is the weaker compared to ionic bonding. Okay, so that's one difference is you get difference in carrier concentration because of their bending, because of their bonding. Okay, other than bonding, okay, what are the other factors which determines these conductivity values?
So,
हाँ,
so what is written on the top with before factors? Yes.
primarily factors. Okay, major, or you can write major factors. Okay, major factors or primarily major factors which define, okay, which define your concentration. Okay, conductivity values. Now other things also have, like your crystal. Okay, whether your sample is single crystal, okay, polycrystalline, solid can be single crystal, polycrystalline. It can be also amorphous. So these factors will also determine your conductivity values. Okay, but here we are not discussing these factors. Okay, we are assuming my silicon, my germanium, they are single crystal. Okay, if they are polycrystalline sample, then there will be grain boundaries. Okay, and that will also affect your conductivity, which we are not discussing in this course. Okay, amorphous means there is no arrangement of there is a not regular arrangement of atoms. Okay, amorphous material have a generally very low conductivity compared to your single crystal and polycrystalline materials. Okay, so this is also one factor which determines the conductivity. Then of course there is a arrangement of atom. Okay, arrangement of atom in crystal. Okay, what is the crystal structure? Okay, that also governs. Okay, that also determines coercive forces. Okay, what will be the coercive force? Okay, so that also defines your conductivity values. Okay, so these are the points which I want to discuss. Okay, now one more major factor which we major things which we use while we use semiconductors, that is band structure. Okay, so I'm drawing your simplest energy band diagram. So if you see, this is my valence band, this is my conduction band. So in the case of insulator, this band gap is very high. Okay, so around order of 6 to 8 electron volt. Okay, very high. Okay, if you see your this is insulator. Okay, if you see this much, this was for your semiconductor. Okay, so they have 1 to 3 electron volt. Okay, this is valence band, conduction band. For example, if you say silicon, okay, silicon has a band gap of 1.1 electron volt. Germanium has 0.6 electron volt. Okay, and if you see metal, okay, so in the case of metal, there is a overlapping between conduction and valence band. Okay, so that's why you got very high conductivity of concentration of electron in the conduction band in the case of metal. Okay, while if you want to get here the carrier concentration conduction band, you need to supply some energy in the form of temperature. Okay, or voltage. Okay, so if you want to increase the conductivity of your semiconductors. Okay, so these are the differences you already know, you studied in your schools. Okay, so EZ is almost 0. Okay, in the case of your semiconductors. Okay, so this is the classification based on your band gap. Okay, now I know the conductivity formula. Okay, so I know my conductivity is sigma is equal to n mu e. Just now we have seen this is the conductivity of a solid. Okay, while if I take a semiconductor, okay, in semiconductor I have electron as well as a whole charge carriers. So if I want to write a expression for a semiconductor, I have to write n e, okay, mu n, okay, and for the holes, concentration of holes, okay, e mu p. So if I want to calculate, a conductivity of a semiconductor, what I need mobility values and carrier concentration values. If I know these values, I can estimate the conductivity of my sample. Okay. Similarly, if I want to study the temperature variation of conductivity, okay, how conductivity varies with temperature, okay, then I should know how concentrations vary with temperature, how mobility varies with temperature. When we know this, the dependence of carrier concentration mobilities on temperature, so then we can calculate what is the dependence of conductivity on temperature. Okay, so first of all, we discuss now by semiconductors. Okay, intrinsic semiconductors. Okay, so we know semiconductor can be classified. So I'm going quickly through this because these things you already know. Okay, I want to directly come to main point, so where we have to solve the problems. Okay, so semiconductor is intrinsic. Okay, semiconductor is extrinsic. Okay, so in pure form, they are called intrinsic semiconductor. When you add some impurity, their semiconductors are called your extrinsic semiconductor. Okay, for example, if I take silicon, okay, so silicon the electron configuration, silicon, the atomic number is 14. So if I write silicon, this is 1s2, 2s2, 2p, 2p, 6, 3s2, 3p2. Okay, so they have 4 valence electron in the atom of silicon. Okay, so what they do, they make bond. Okay, so they make bond with 4 neighboring atoms. Okay, so this is my silicon. So they share these electron with neighboring atoms. Okay, and they form the bond. And if you see at T is equal to 0 Kelvin, okay, all the electrons are in valence band. Okay, all the no electron is free at T is equal to 0 degree Kelvin. Okay, that means if I draw my conduction band, this is my valence band, this is my conduction band. Okay, this is the energy axis. Okay, so if I see my all the electrons are bound, okay, with atoms. Okay, so they are in valence band, and conduction band is completely empty. Okay, at T is equal to 0. Okay, so your pure semiconductors or intrinsic semiconductors, they behave like an insulator at T0 Kelvin. Okay, so at T is equal to 0 Kelvin, okay, intrinsic semiconductors okay, behave like insulator. Okay, because conduction band is completely empty. Okay, now if you supply some energy, okay, if you supply some energy and material also has some defects, if it's not a perfect crystal material and you're applying some temperature, okay, what will happen? Because of this energy, okay, some bond will break. Okay, suppose this bond breaks, okay, and this electron will become free, so this become hole, and this electron is become free electrons. So as you increase the temperature, what will happen? Some of the electrons from the conduction band start moving towards the valence band. So they leave hole here and electron come here. Suppose 2 electrons are going, so there will be 2 holes. Okay. So this happens in the case of internal semiconductor. That means in an internal semiconductor, the concentration of electron in conduction band is equal to the concentration of hole in the valence band. So I can write the concentration of hole in electron by Ni, okay, or concentration of holes, say N, a concentration of holes in valence band, they are both are equal, okay, in the case of semiconductor, and that is equal to intrinsic carrier concentration. Okay, so this is my intrinsic semiconductor. Okay, what happens when I make extrinsic semiconductor out of this intrinsic semiconductor? So in order to make extrinsic semiconductor, what I will do, I will dope this, I will replace this silicon with some impurity atom. Okay, so if I replace this, so this silicon is in the group 4, okay, because there are 4 valence. I just now shown you in electronic configuration. So if I replace this silicon atom, okay, in some mole percent, okay, suppose I want to 1 atomic percent or 2 atomic percent सिलिकन आई वांट टू रिप्लेस. ओके, 100 में से 1 रिप्लेस कर दिया. ओके, 100 में से 2 रिप्लेस कर दिए with some 5th group element like antimony, arsenic, okay, which is a 5th group element. So this 5th group element will have a 1 extra electron, okay, which will be very loosely bound. Okay, so these are example of n type of material, n type of semiconductor. Okay, so what will happen when you dope replace the silicon with some element of 5th group? Okay, so these electrons are very close to conduction band. So the energy level of this donor atom, okay, so the energy level of this donor atom, okay, these are donor atoms. Okay, in the case of anti-material, water impurity, if you are adding 5th group impurity, that element will give its electron to the crystal. Okay, so that's why it is called this is a donor. Okay, so I will represent by them Nd. Okay, donor atoms. Okay, So these are donor atoms. So the energy levels of donor atoms are very close to the conduction band. Okay, so even if we apply little bit energy, what will happen? These donor will get ionized. These donor will get ionized, and they will give their electron to the conduction band. Okay, because if you want to bring electron from valence band to conduction band, okay, this energy, this band gap, this is the difference between a conduction band and a valence band, is band gap, and this energy is very high. While this is very close, around 0.01, 0.02 electron volts. Okay, this is 1 electron volt, 2, 3 electron volts. So you need very high energy. Okay, while if you dope this element, okay, at room temperature itself, these atoms will get ionized, and you'll get in enhanced conductivity for n-type semiconductor. That means your conductivity value will be increased in orders. Okay, suppose you have 10 to 5 5, you can come from 10 to 5 to 10 to 5 power minus 3 in the case of silicon. Okay, so by just by replacing some atoms, okay, in the crystal, okay, by impurity, you can get a wide range of conductive values in the case of semiconductors. Okay, so this is n-type material. Same happens in p-type material. Yes,
सर मेरा कनेक्शन चला गया था सर. कैन यू जस्ट रिपीट व्हाट यू जस्ट टोल्ड?
hello,
30 सेकंड्स तक गया था सर. हेलो हेलो
so I'm
हेलो.
discussing. Am I audible now?
यस सर, यू आर
So-
ऑडिबल नाउ.
Hello, Puneet, can I continue?
यस सर. सर वो कह रहा था कि
Varun?
आपने सर आपने जो 30
Am I
सेकंड पहले
audible?
तक, सर मेरी आवाज आप तक आ रही है सर? हेलो
Am I audible, Gurleen?
सर के पास हम लोग
Yes,
की
sir.
आवाज नहीं जा रही है.
हमारी आवाज नहीं आ रही.
Nobody is replying. Okay.
सर के पास हम लोग की आवाज नहीं जा रही है.
Okay. Thank you. So now what happens? So this is the case of n-type material. When you dope n-type semiconductor with n-type, so impurity of fifth group element. Okay. So then you will get this conduction band with room temperature. These atoms can ionize and they can provide the electron to conduction band. Okay. Similarly, if I use this
हेलो
boron or aluminium, okay,
हेलो.
say aluminium, okay, or third group element, okay, so these are so what will happen? They have only 3 electron to share, so there will be holes in the valence band. And if I see the energy level of these acceptor atoms, because now they will accept the electron, okay, that's why they are acceptor. So I'm representing them by EA. These are acceptor atoms, okay, E acceptor atoms, EA. So the energy level of acceptor atoms are very close to the valence band. So what will happen? Suddenly at room temperature, what will happen? These electron will capture the electron from the valence band. Okay, so they will generate holes in the valence band, and they will become negatively charged. Okay, so that's why they are acceptor ions. They will become acceptor ions. These become donor ions. Okay, so this happens in the case of when you're doping any element of third group.
हेलो
These are the
हेलो
p-type
हेलो.
material. Okay, so in the case of n-type material, you have majority charge carriers. Okay, in the conduction band, those are electrons, and they are reside in conduction band. Okay, while in the case of p-type material, your majority charge carriers, the carriers are in valence band holes. Okay, so this is the difference between intrinsic and extrinsic semiconductor. Okay, now what is my aim? My aim is to find out. So this is my expression, Ne mu n plus Pe mu p. Okay, so my first aim is to find out the concentration of Np. What are the expression for N and P? Okay, so I'll calculate what are the N is the concentration of electron in the conduction band, P is the concentration of hole in the valence band. Okay, so let me calculate these values. So put the heading. So how much time is giving? Okay, put the heading concentration of electron.
सर
Concentration. So let me drive some formulas today. Okay, and for tomorrow onwards we'll solve the problems. Okay,
हेलो
so concentration of electron in conduction band. Okay, so I want to calculate the concentration of electron in the conduction band. Okay, so how can we calculate the concentration of electron in conduction band? Can anyone tell? कैसे निकालेंगे?
Hello, hello, sir. Are you audible?
कैसे निकालते हैं
Hello.
कंडक्शन बैंड में इलेक्ट्रॉन
Hello.
concentration? So
सबसे पहले
we
तो
can
सर
calculate
स्टेट
the concentration of
सर
electron in
हम
the
लोग को नहीं
conduction
सुन
band
पा रहे हैं.
हाँ
if
सर
we
सबसे
know the
पहले
density of
स्टेट
states. Okay, if I know the density of state in conduction band, okay, and if I know the probability of occupation of electron in the conduction band, then I can calculate the density of the number concentration of electron in the conduction band. If I integrate this equation from zero from EC to infinite, GCE, FE, DE, I can calculate the concentration of electron in the conduction band. Okay, now try to understand this expression. Okay, जैसे सपोज मुझे एक क्लास में स्टूडेंट को काउंट करना है कि कितने स्टूडेंट बैठे हैं. Okay, indirectly count करना है. I don't want to count one by one. Okay, I want to count for some other way. So I should know what is the density of seats. Okay, suppose in a class there are 10 rows. Okay, and each row is one energy level. Okay, and I want to calculate what is the how many number of students are sitting in the classroom. So what I will do, I'll calculate density of states. Okay, density of state in each row में कितनी states हैं. Okay, and once I know the states per line, once per energy level states, once I multiply this expression by probability, I can know how many students are sitting. For there are, suppose there are 100 seats and the probability is of occupying the seat is 0.5. So I can multiply by 100 seats into 0.5. I will 50. I know in each level there are 50 students. Okay, so if I know each one level there are 50 students, there are 10 rows. I can integrate. I can add them. Okay, so this is the way to calculate the concentration of electron in conduction band. Okay, so I'm repeating again. If I know density of state, okay, that is number of state per unit energy per unit volume. Okay, if I know the number of states per unit energy per unit volume, and if I multiply them my Fermi Dirac function. Fermi Dirac function is the function which shows the probability of occupying an energy level. Okay, the probability that an electron will occupy energy level, उसकी probability क्या है? If I know the density of state, I know the probability, I can integrate this expression and I can calculate what is the concentration of electron in the conduction band, what is the expression for concentration of electron bond for a given semiconductor. Okay, and GCE that will be discussed with you in statical mechanics course. Okay, derivation. GCE is given by the density of state. The expression is 4 pi h cube 2 mn 3/2 E minus EC power half. Okay, this is the expression for density of states in a conduction band where your mn क्या होता है? What is mn?
इफेक्टिव मास.
Your mn is effective mass of electron. Okay, effective mass of electron in the crystal. These are the expression. Okay, now what is Fermi Dirac function?
Hello.
What is Fermi Dirac function? कितना होता है? वैल्यू क्या है?
1 होता है सर.
Fe?
Fermi Dirac तो
to the power E minus EF plus 1 upon K plus
What
1.
is Fe? So your
Hello, sir. Are
Anyone?
you audible? Am I audible?
what is Fe?
Am I audible, sir?
So your Fe is 1 upon 1 plus exponential E minus EF upon KT. This is the expression for your Fermi Dirac function. Okay, so now I want to use this expression as well as this expression together. I want to integrate this one. I want to calculate the concentration of electron in the conduction band. Okay, for that I need to simplify this expression. Now just see, this is my conduction band, this is my valence band. Okay, and my Fermi level is somewhere here in between, between them. Okay, by this one we can show the Fermi level is somewhere between conduction band and valence band. Now E minus EF. Okay, I want to calculate energy levels. I want to calculate the number of electron in conduction band here. Okay, that means my energy is here. This E minus E minus EC. Okay, E minus EC. That means my E is above the conduction band. So this is called bottom of the conduction band, and this is the top of the valence band. Okay, so since I want to calculate the electron concentration here, that means my all levels will be greater than EC. Okay, that means this EC minus EF. Okay, this EC minus EF will be greater than this KT. KT की वैल्यू कितनी होती है at room temperature? If I say room temperature KT, okay, so KT value is around 25 or 26 milli electron volt. 25 to 26 milli electron volt, because my K is 1.38 into 10 raised to power minus 23 joule per second, joule per Kelvin. Okay, and T is by 300 Kelvin. Okay, so if I multiply this, I can calculate in joules, and if I convert this joules into electron volt, so this is the room temperature energy. Okay, now अभी वॉल्यूम आ रही कि नहीं आ रही है?
Hello, sir. Are we audible to you?
Okay.
Hello.
Am I audible or not?
So you are audible, but we are not audible to you.
Okay. So this is my this KT value. Okay. Now compared to this KT, if I'm considering my conduction band, compared to this KT, this E minus F is greater than this KT. Okay. So if I'm in conduction band, this my E minus EF is greater than KT. Why? क्योंकि फर्मी लेवल तो यहाँ पर है, कहीं पे बीच में है. सपोज ये 1 इलेक्ट्रॉन वोल्ट है, सपोज फर्मी लेवल यहाँ बीच में है या इधर कहीं पर है, तो ये डिफरेंस एटलीस्ट 500 मिली इलेक्ट्रॉन वोल्ट से ज्यादा है. Okay, so 500 milli electron volt is greater than this 26 milli electron volt. So whenever you are in conduction band, your E is E minus EF is greater than KT. Okay, so that means this exponential, suppose E minus EF is greater than by 3 KT. Okay, 2 KT, 3 KT, 4 KT, then this exponential term will dominate. Okay, that means in the expression of this Fermi drag, I can neglect this one. Okay, so my Fe in the case of if I'm in conduction band, my Fe will be, okay, I can neglect this one and this become exponential, okay, minus E minus EF upon KT. Okay, so now I know density state, this formula, I know Fermi drag density function. Just multiply, integrate, you can get the concentration of electron in the conduction band. Okay, so I'm deriving this one now. So say I want concentration of electron in conduction band. Okay, so that is GCE. Okay, so GCE is 4 pi h cube 2 mn 3/2 E minus EC. Okay, so I'm telling this is half. So this is, say this Cn. Okay, and this is E minus EC power half. Okay, so if I put this value here, Cn E minus EC power half. Okay, and then I have Fe. Fe this one exponential. Okay, minus E minus EF by KT d. This become my, now solve this integration. Okay, just solve this integration. from EC to infinite, because my bottom is EC. I want electron here, EC to infinite. Okay. Solve this integration.
Sir, half KT के बाद 3/2.
Hello,
Hello.
sir. Hello, sir.
So put E minus EC is equal to X and solve this one. So if I put this values N, Cn, okay, E minus EC, so when E is equal to EC, X is equal to 0. So this becomes 0 to infinite, limit Cn, this become X power half, okay, this become exponential minus X, okay, dx into क्या आएगा? Suppose I am putting this one here, this become X power half, okay, so d equal to dx, okay, so exponential minus e की जगह रखना है मुझे EC plus x, EC plus x, x plus EC minus EF, okay, upon KBT, KT जो भी है KBT और KT, okay, d की जगह dx. So if I solve this integration, I'll get n equal to Cn 0 to infinite, okay, x power, if I इसको बाहर निकाल दो, EC कांस्टेंट है, EF कांस्टेंट है, तो एक्सपोनेंशियल, ओके, माइनस EC माइनस, ओके, यहाँ पे KBT भी ले लो, ओके, E माइनस EC अपॉन KBT को x मानोगे, ओके, सो यहाँ से आ जाएगा x पर हाफ KBT हाफ, तो एक्सपोनेंशियल EC माइनस EF KBT, and this you will also get KBT power 3/2, okay, and integration x power x e power minus x dx from 0 to infinite, okay. This is just derivation, you can find in notes and books also, okay. इस इंटीग्रेशन का वैल्यू कितना होता है? x power half e power minus x dx. What is the value of this integration?
Half root pi होगा sir. Half root pi. Sir, half root pi होगा sir.
Half root
Upon
pi.
root pi.
सर सुन ही नहीं पा रहे हैं.
किसको पता है इसका वैल्यू?
देखिए सुन नहीं
So
पा
the
रहे
value
हैं.
of this integration is, okay, root pi by 2, okay, so I can put this values. Now I know this Cn is 4 pi, okay, h cube 2 mn power 3/2, okay, KBT also coming here, KBT power 3/2 coming here, and then it's coming root pi by 2, and then it's coming exponential minus ES minus EF upon KBT, okay. So if I solve this one, okay, I can write 2 to cancel, pi here, half pi here, 3/2 pi, so I can write this one 2 pi mn, okay, KBT upon h square power 3/2 exponential minus EC minus EF upon KBT, okay, and if I simplify, write in simple terms, okay, so I can write the concentration of electron in conduction band is given by NC exponential minus EC minus EF upon KBT, okay. So this is the formula for concentration of electron in the conduction band, okay. So बड़ा आसान है, इसको याद रखना, okay. आपको पता है EC यहाँ पर है, okay, EF यहाँ पर है, तो ये टर्म जो हमेशा पॉजिटिव होनी चाहिए, EC माइनस हमेशा पॉजिटिव होनी चाहिए, okay. So with जैसे जैसे EC बढ़ता जाएगा तो concentration इलेक्ट्रॉन कम होता जाएगा, that's why there is a minus, okay. So this is a very important expression and these are the general expression, okay. इसमें कुछ intrinsic नहीं है, extrinsic नहीं है, this is the general. I have one semiconductor, एक semiconductor है जिसका बैंड गैप मुझे पता है, जिसका ईसी पता है, ये भी पता है. सो दिस इज, हेलो, हाँ वो मुझे समझ में नहीं आ रहा, क्यों नहीं आ रही है. अच्छा मैं चेक करता हूँ. Am I audible now?
यस सर।
आप ऑडिबल है लेकिन
हेलो
शायद
सर सर,
हाँ तो अब तो
आर
तुम्हारी
वी
आवाज भी आ रही
ऑडिबल
है.
टू यू?
पहले भी आ रही थी तुम्हारी आवाज तो. सो
सर आपने
आ
रिएक्शन
रही
नहीं दिया
थी।
ना सर एक बार भी.
हाँ,
आपने रिएक्शन नहीं दिया ना सर एक बार भी हमें.
अच्छा
हाँ सर, मुझे भी इतना डाउट्स आया था सर, आप एकदम फ्लो में
अभी
चले
आवाज आ
गए।
रही है. अच्छा तो क्या डाउट है बता दो, अभी कुछ याद है तो बताओ. तो ये मैंने अभी एक्सप्रेशन ड्राइव किया है, the concentration of electron in the conduction band. Okay, so where nc is a constant, when nc is 2 pi mn kbt h square power 3/2. Okay, हाँ आप पूछो क्या क्या डाउट था बताओ. आलोक क्या डाउट है बेटा? हेलो.
सर वो सिलिकॉन वाले में था सर कि
हाँ.
ये कंडक्शन बैंड और वैलेंस बैंड 0 केल्विन पे, और फिर उसको बढ़ाते हैं तो उसका क्या स्टोरी है सर?
भी पहले आपका जो सिलिकॉन सिलिकॉन का वैलेंसी 4 है, ठीक है. उसके बाद 4 इलेक्ट्रॉन है. वो चारों इलेक्ट्रॉन वो क्या है, वो सराउंडिंग एटम के साथ शेयर कर लेता है, ठीक है.
ओके
इट मीन सारे इलेक्ट्रॉन बाउंड है, सारे के सारे इलेक्ट्रॉन, सारे के सारे इलेक्ट्रॉन वैलेंस इलेक्ट्रॉन है. ओके, सो नो इलेक्ट्रॉन इज अवेलेबल एट कंडक्शन बैंड एट t is equal to 0 केल्विन. ओके, जैसे ही यू सप्लाई द एनर्जी, ओके, तो क्या हो जाएगा, सम बॉन्ड विल ब्रेक, और सम बॉन्ड ब्रेक करने के बाद में क्या हो जाएगा, कंडक्शन इलेक्ट्रॉन कंडक्शन बैंड से वैलेंस बैंड में चला जाएगा, तो कनेक्टिविटी बढ़ जाएगा टेम्परेचर के साथ में. दैट्स व्हाई योर कनेक्टिविटी और कैरियर कंसंट्रेशन जो होती है सेमीकंडक्टर की, वो टेम्परेचर पर डिपेंडेंट होती है. ओके, टी इज इक्वल टू 0 पे 0 इलेक्ट्रॉन है, कनेक्टिविटी नेग्लिजिबल है. ओके, और 0 बोल दो 0 है, एंड देन एज इंक्रीज द टेम्परेचर, ओके, यू गेट मोर एंड मोर इलेक्ट्रॉन इन कंडक्शन बैंड. सो इंट्रिंसिक सेमीकंडक्टर के केस में आपकी कंडक्टिविटी हमेशा बढ़ती जाती है, टेम्परेचर के साथ में हमेशा बढ़ती जाती है. ठीक है, विल सी द प्लॉट व्हेन विल ड्रॉ इन द केस ऑफ इंट्रिंसिक सेमीकंडक्टर. ओके, और
ओके सर, और सर ये डेरिवेशन में यू हैव टोल्ड वन पॉइंट कि ये डेंसिटी से मल्टीप्लाई कर रो कॉलम, उसका क्या था सर?
डेंसिटी में क्या है भी, अगर अगर मुझे कोई नंबर चाहिए, ठीक है ना, अगर मुझे मुझे चाहिए नंबर ऑफ इलेक्ट्रॉन कंडक्शन में चाहिए, तो अगर मुझे डेंसिटी ऑफ स्टेट्स पता है कि पर यूनिट एनर्जी में कितनी स्टेट्स हैं, ठीक है, और उनकी ऑक्यूपेंसी पता है, प्रोबेबिलिटी क्या है, प्रोबेबिलिटी पता है उनकी उनकी ऑक्यूपेंसी की इलेक्ट्रॉन स्टूडेंट बैठे हैं क्लास में, कितनी प्रोबेबिलिटी है. अगर 0.5 है तो नंबर ऑफ सीट्स को मैं 0.5 से मल्टीप्लाई कर दूंगा, मुझे नंबर ऑफ इलेक्ट्रॉन नंबर ऑफ स्टूडेंट मिल जाएंगे क्लास में. Okay, so if I know the density of state expression, and if I multiply by Fermi-Dirac distribution function, okay, Fermi-Dirac distribution function क्या बताता है कि कोई चीज भरी हुई है कि नहीं है, इलेक्ट्रॉन वहां पे बैठा हुआ है कि नहीं बैठा हुआ है, उसके बैठे रहने की या उस स्टेट को ऑक्यूपाई करने की प्रोबेबिलिटी कितनी है, दैट इज गिवन बाय Fermi-Dirac distribution function. तो अगर मुझे स्टेट्स पता है और मुझे probability पता है, if I multiply both these things I can get the number of electron. Okay, एंड जो डेंसिटी ऑफ स्टेट का एक्सप्रेशन है वो मैंने यहाँ पे ड्राइव नहीं कराया है. ओके, दैट विल यू विल डू इन स्टैटिकल मैकेनिक्स. ओके, the Alok sir will do that. So I have directly used the expression for density of state. I will use this Fermi-Dirac distribution function. I have multiplied them. I have integrated them from EC to infinite, and we finally come to conclusion. This is the expression for the concentration of electron in the conduction band. Okay.
Okay sir.
Now
Thank you, sir.
similarly I want to calculate the concentration of holes in the valence band. Okay, so I think there's no time today, so that is homework. Okay, so concentration of holes concentration of holes in valence band. Okay, if you solve this one, you'll get P is equal to NV exponential minus EF minus EV upon KBT. This expression you will get for holes, and I'm reminding again. Okay, these are the general expression. Okay, ये ऐसा नहीं है intrinsic का या extrinsic का है. These are the general expression for intrinsic case. Okay, now what will happen to intrinsic extrinsic case we will discuss. So in order to calculate the number of holes in the valence band, okay, you need the density of states, okay, in valence band, and that is given by EV minus E power half, okay, Cp, and where Cp is what we written earlier, 4 pi h cube 2 mp 3/2, okay. And in the case of अभी हमको चाहिए concentration of holes in the valence band, तो जो Fe क्या करता है, Fe दिखाता है the probability of occupying electron, okay, और हमको चाहिए hole की probability, the hole की probability हो जाएगी 1 minus Fe, okay. So you have to use now, this is the density of state expression, and you have to use 1 minus Fe, so 1 minus exponential E minus EF upon KBT, okay. Now again you have to take the case. Now you are in a valence band, you are here, and your Fermi level somewhere here, okay. That means, sorry, this is Fe is 1 plus x, okay. So if you solve this one, this will give you 1 minus 1 plus exponential E minus EF upon KBT, okay, minus 1, okay, and this is 1 plus exponential, okay. अभी छोड़ो, कल ही करेंगे इसको. So now you have to, instead of Fe, you have to take 1 minus Fe, and you have to integrate this equation, okay, from minus infinite to EV, okay. Your GVE and 1 minus Fe d, you have to solve this integration, and I told you the answer will come your P is equal to NV, okay, exponential minus E, because it's the valence band, so EF minus EV, so EF minus EV upon KBT, okay. So tomorrow we'll discuss this formula and start solving the problems, okay. अभी कोई क्वेश्चन तो पूछो if you're in doubt.
1 minus Fe क्यों करा सर?
1 minus Fe क्यों करा? क्योंकि ये क्या है, इलेक्ट्रॉन के पाए जाने की प्रोबेबिलिटी, और इलेक्ट्रॉन मिसिंग है उसकी प्रोबेबिलिटी क्या है, इलेक्ट्रॉन मिसिंग होने की प्रोबेबिलिटी 1 minus Fe है, तो इलेक्ट्रॉन मिसिंग है इसका मतलब क्या, होल प्रेजेंट है.
अच्छा,
okay. So the derivation what I have done, you have to do same derivation, okay. Now taking 1 minus Fe, of course you have to apply the limits also, what happens, okay. So try this. हाँ
सर, इसमें जो एनर्जी वाला टर्म होगा सीपी में, वहां पे सर ईवी माइनस ई लिखा जाएगा.
कहाँ पे?
तो जैसे सीपी इक्वल टू 4 पाई एच बाय एच क्यूब इनटू
ये तो कांस्टेंट है साथ में ये वाला, और ये ईवी माइनस ईवी माइनस हाफ है, ठीक है.
ओके सर.
और आपको ये 1 minus Fe भी सॉल्व करना पड़ेगा, ओके. 1 minus Fe कैसे सॉल्व करोगे? 1 minus Fe भी देख लो एक बार, क्योंकि इसी में मिस्टेक आएगी. 1 minus Fe 1 minus, okay, this is 1 plus exponential, okay, minus sorry, E minus EF upon KBT, okay. So E minus EF पॉजिटिव है कि नेगेटिव है?
नेगेटिव
है, क्योंकि हमारा फर्मी नेगेटिव है ना, हमारा फर्मी लेवल यहाँ पर है, ठीक है. और ये इधर है, नेगेटिव है, ठीक है. और तो ये माइनस नेगेटिव हो जाएगा, ठीक है. बट सर मिस्टेक इज कमिंग, आई डोंट नो वेदर आई एम राइटिंग फॉर्मूला करेक्ट और नॉट करेक्ट. सो if I write this one as a 1 plus exponential E minus EF by kBt, okay, minus 1, okay, and 1 ये तो से आ गया 1 plus exponential e minus ef kBt, okay. So now since this is infinite minus infinite, क्योंकि ये टर्म नेगेटिव है and e is very greater than ef, so this term become almost minus infinite, okay. So this term becomes 0 because power e exponential power minus infinite because this term is negative, okay. Your e is less than ef, okay. So this term is become now minus minus infinite, so this term becomes 0, so you can neglect this term instead of in comparison of 1, okay. So your 1 minus fe will come only this much, so your 1 minus fe will come only this much. अब इसको लेके इंटीग्रेट कर दो, ठीक है, इंटीग्रेशन होगा माइनस इनफाइनाइट टू ईवी, सेम प्रोसीजर है, करोगे तो तुम्हारे पास आंसर आ जाएगा, you will get the concentration of holes in the conduction band, okay. So once you know the concentration of holes in electron, okay, tomorrow I will start solving the problems on semiconductor, okay. Thank you very much.
Okay, sir.
अगर कोई डाउट है, आज क्लास में डाउट है, you can come tomorrow I will discuss, okay. Initially 5-10 minutes we'll discuss this doubts, okay.
Yes, sir.